Hi everybody, welcome to Dr. Manny's YouTube Learn Shops. This is part 3, the concluding session of Inferential Statistics, where we look at data analysis techniques. The learning objectives for this session are to review basic statistical methods to analyse data, discuss skills for basic data analysis, and review basic skills to interpret data. So when we look at the concept of data analysis, this is a process of systematically applying statistical and or logical techniques to describe, illustrate, condense and review and evaluate data. It's a process of inspecting, cleaning, transforming and modelling the goal of discovering useful information, informing conclusions and supporting decision making. According to Shamu and Resnick in 2003, they state that analytic procedures are a way to provide a way for drawing inferences from data and distinguishing the phenomenon of interest from the statistical fluctuations present in the data. So when we look at statistical data analysis, this is a procedure of performing various statistical procedures. It's a kind of quantitative research which seeks to quantify data and typically applies some form of statistical analysis. Quantitative data basically involves descriptive data such as survey data and observational data, and it involves statistical tools and requires statistical knowledge, and there are various software packages that perform statistical data analysis, which you'll be covering with your coordinator. And this involves software such as the Statistical Package for Social Sciences, SPSS. So when we look at data analysis, there are issues. Your considerations before doing it should be having the necessary skills to analyse the data, selecting appropriate data collection and analysis methods, drawing unbiased inferences, following acceptable norms for disciplines, determining statistical significance and providing honest and accurate analysis, and consider the manner of presenting the data, data recording method, reliability and validity, and the extent of the analysis that you want to do. Here's an example of the research process using statistics. And the populations are 2 first grade students, groups, sample A and B. So in step 1, the experiment is to compare the 2 teaching methods. Step 2, test the scores for the students in each sample. 3, organise and simplify. Step 4, interpret the results. So what you've got here, sample A, taught by method A, sample B, taught by method B. Sample A has an average score of 76, sample B has an average score of 71. So the sample data shows a 5-point difference in the teaching method outcomes. However, there are 2 methods that you can use to interpret the data. In one, there's no difference in the teaching methods and sample data due to chance or sample error, or 2, there is a difference in the teaching methods and sample data which reflect the difference as accurately. Note that the aim of the inferential statistics is to assist the researchers to decide between the 2 possible interpretations. When we look at the null and alternative hypothesis, in inferential statistics, the test, the alternative hypothesis, if true, the null hypothesis is not. The researcher has a criterion for making the decision by setting the significance level generally at 0.05. If the 0.05 level is achieved, the p-value is less than or equal to 0.05 or 5%. Then the researcher rejects the null hypothesis and accepts the alternative hypothesis. If the 0.05 significance is not achieved, then the null hypothesis is retained. Using probability theory for the test, the researcher can assess how likely the difference found is real and not due to chance. The level of significance in inferential statistical testing, This is where the researcher always sets a significance level for each statistical test that they conduct. By using probability theory as a basis for their tests, researchers can assess how likely it is that the difference they find is real or not due to chance. If the probability of the results occurring by chance is below a certain level, p-value is less than or equal to 0.05 or 5%, we assume that these results will be significant. We need to talk about the degrees of freedom. And broadly defined, the degrees of freedom is the number of observations in the data that are free to vary when estimating statistical parameters. It refers to the maximal number of logical independent values, which are values that have the degree of freedom or the freedom to vary in the data sample. To calculate the degrees of freedom, subtract the number of relations from the number of observations. For determining the degrees of freedom for a sample mean, subtract 1 from the number of observations. Examples could be chi-square, ANOVA, as far as the calculation formulas go. When choosing a statistical technique, the most important steps are to consider what are the independent and dependent variables of the study. How are each of the variables measured? And then you can choose the statistical procedure that will be best to answer the study questions. Additional factors to consider are the research design, the aim of the research, the types of the data, and the hypothesis. So, an example to consider. There are 5 students are asked to design a study that will assess the relationship using the Y2 Fit exercise video and weight loss in a group of 150 overweight preteens during a month-long period. The weight of the participants is taken at the beginning and at the end of the study. The students come up with 5 different proposals. Student A proposes to randomly assign half of the group to the video intervention. This group will be instructed to do video fitness aerobics for 30 minutes 5 times a week, and the other half would serve as a control and will not be told to do anything. Student A wants to determine whether using Y-Fit would lead to weight loss. Accordingly, suggests that the participants be classified into one of 2 groups, no weight loss and weight loss. Student B also proposes to randomly assign half the group to the WIFE video aerobics intervention, and this group will be instructed to do video aerobics 30 minutes 5 times a week, and the other half would serve as control or be told not to do anything. Student B then wants to determine whether using the Fit would lead to weight loss, thus suggests that weight loss should be defined in terms of difference in weight prior to and immediately after the study. Student C proposes to randomly assign 30 preteens to one of 4 types of WIFE interventions: aerobics, yoga, strength training, and balance games. These 4 groups will be instructed to do Fit activity for 30 minutes 5 times a week, and the last group of 30 preteens would serve as a control and not be told to do anything. Student C then wants to determine whether using Fit would lead to weight loss, thus suggests that weight loss should be defined in terms of the difference in weight prior and immediately after the study. Student D proposes to simply ask the 150 overweight teens to record the number of minutes per day they spend using Fit, and then suggests that the participants be classified into one of 2 groups, no weight loss and weight loss. Student E also proposes to simply ask 150 teens to record the number of minutes per day they spend using Fit, and then suggests that weight loss should be defined in terms of the difference in weight prior to and immediately after the study. The example, the first objective is, in the variables of the study, what are the variables of the study? the width fit would be the independent variable, weight loss would be the dependent variable in the study. Second objective, the definition or measurement of the variables. There are several ways to define the measurement, the independent and dependent variables of the study. But there are two main questions to consider. Is the independent variable measured categorically or continuously? And is the dependent variable measured categorically or continuously? Student A defined the Y-fit use in terms of using the Y-fit and not using the Y-fit, and accordingly defined the Y-fit use in terms of categories and defined the weight loss in terms of no weight and weight loss. Thus, the definition of weight loss was categorical. Student B also defined the WF-fit use in terms of using the WF-fit or not using the WF-fit, thus defined the WF-fit use in terms of categories and defined weight loss in terms of the difference between weight prior to the study and weight immediately after the study. Weight loss was therefore defined continuously. Student C defined Y-fit use in terms of type of Y-fit activity, thus defined Y-fit use in terms of 5 categories. Also defined weight loss in terms of the difference between weight prior to the study and weight immediately after the study. Weight loss therefore was defined continuously. Student D defined Y-fit use in terms of the number of minutes per day spent using the Y-fit, such as Y-fit use was defined as continuously. He defined weight loss in terms of no weight or weight loss. Thus, the definition of weight loss was categorical. Student E defined the Y-fit use in terms of the number of minutes per day spent using the Y-fit, such as Y-fit use was defined continuously. Also defined weight loss in terms of the difference between weight prior to the study and weight immediately after the study. Weight loss therefore was defined continuously. The third objective that we have to consider is choosing the appropriate statistical approach. Student A could choose to perform either a cross-tabulation analysis or logistic regression procedure. Both tests are useful when the independent and dependent variables are measured categorically. Student B would need to conduct an independent t-test procedure, since the independent variable would be defined in terms of categories and the dependent variable would be measured continuously. An independent t-test procedure is used only when the independent variable has 2 categories. Student C would need to conduct a one-way ANOVA, since the independent variable will be defined in terms of categories and the dependent variable would be measured continuously. A one-way ANOVA is used when the independent variable has 3 or more categories. Student D could use logistic regression procedure to analyse his data, since his independent variable would be measured continuously and his dependent variable would be measured categorically. If student D defined the dependent variable in terms of 3 or more categories that could be ranked as weight gain, no weight loss, then an ordinal regressional procedure would be used. Student D could choose to perform either a Pearson's correlation procedure or a linear regression procedure, since both variables would be defined continuously. Usually a correlational test is conducted when there's only one independent variable and one dependent variable. If student E wanted to study the relationship between several independent variables, number of hours spent sleeping, number of calories consumed per day, and weight loss, then using a linear regression procedure is required. This just demonstrates the importance of choosing the correct tools when you do your research. Data measurement levels are also important, and these are levels of measurement, also called scales of measurement, which inform how precisely variables are recorded. In scientific research, a variable is anything that can take on different values across the data set, such as height or test scores. There are 4 levels of measurement: nominal, ordinal, interval, and ratio. An example of a nominal level would be where you can categorize your data by labeling it in mutually exclusive groups, but there's no order between the categories. So for example, the city of your birth, your gender, ethnicity, car brands, marital status. Here's an example that you can consider. Which newspaper do you read regularly? What is the appropriate measurement of central tendency for this request as a nominal level? How would you measure it? The measurement would be mode. Then you've got ordinal levels. And here you can categorize and rank your data in order, but you cannot say anything about the intervals between the rankings. Although you can rank the top 5 Olympic medalists, this scale does not tell you how close or far apart they are in number of wins. So examples of an ordinal level would be the top 5 Olympic medalists, language ability meaning beginner or expert, Likert type questions. Here's an example. What grade did you get for each of your subjects? What would be the appropriate measurement for a central tendency for this ordinal level? Median or mode would be appropriate. Then you've got an interval level, and this is when you can categorize rank and infer equal intervals between neighboring data points, but there's no true 0 point. The difference between any two adjacent temperatures is the same. For example, 1 degree, but 0 degrees is defined. So examples of an interval scale would be test scores, such as IQ, exams, personality, inventories, temperature in Fahrenheit or Celsius. So here is an example now of an interval. How fast is your reaction time? What is the appropriate measurement of central tendency for this interval level? This could be the mean, the median, or the mode. Ratio levels. In a ratio level, you can categorize, rank, and infer equal intervals between neighboring data points, and there is a true 0 point. A true 0 point means that there's an absence of the variable of interest. In ratio scales, 0 does mean an absolute lack of the variable. So for example, the Kelvin temperature scale, there are no negative degrees of temperature. 0, however, means an absolute lack of thermal energy. So examples could be of a ratio level: height, age, weight, and temperature in Kelvin. So here's an example. What is your current weight? What is the appropriate measurement of central tendency for a ratio level? The answer would be mean, median, or mode. So to summarize data levels, you have 4: nominal, ordinal, interval, and ratio. And the order of the values is not known in nominal, it's not used. It is known in ordinal and interval and ratio. There's a frequency distribution in all 4. The unit of measurement in nominal is mode, in ordinal, mode and medium, in interval and ratio, all 3: mode, medium, and mean. With statistical analysis, the types of statistical analysis, choosing the techniques is important. And you've got essentially 3: univariate, bivariate, and multivariate forms of data analysis. With univariate, this type of data consists of only one variable, uni. And the analysis of univariate data is therefore the simplest form of analysis, since the information deals with only one quantity that changes. It doesn't deal with cause or relationships, and the main purpose of this analysis is to describe the data and find patterns that exist within it. An example of univariate can be height. So for example, in univariate data analysis, the height of 7 students is recorded. There's only one variable that is height, and it's not dealing with any cause or relationship. So the description of the patterns found in this type of data can be made drawing conclusions using central tendency, measures such as mean, median or mode. Dispersion or spread of data can include range, minimum, maximum, quartiles, variance and standard deviation. And by using frequency distribution tables, histograms and pie charts, frequency polygons and bar charts to demonstrate. Here's an example of a histogram. Bivariate data analysis. This is the type of data that involves 2 variables. And the analysis of this type of data deals with cause and relationships. And the analysis is done to find out the relationship among 2 variables. So an example could be temperature and ice cream sales in the summer season. Temperature, ice cream sales. So if we use an example of bivariate data analysis, temperature and ice cream sales are the 2 variables of bivariate data. Temperature and sales are directly proportional to each other and related. As the temperature increases, sales increase. It's hot, people want ice cream. Bivariate data analysis involves comparisons, relationships, causes and explanations, and variables are typically plotted on an XY axis on a graph for better understanding of the data, and one of these variables is independent while the other is dependent. Ice cream sales and temperature. The hotter it gets, the more sales they have. With multivariate data analysis, when the data involves 3 or more variables, it's categorized as multivariate. And it's similar to bivariate but contains more than 1 dependent variables. The ways to perform analysis on this data depends on the goals to be achieved. Techniques include regression analysis, pathway analysis, factor analysis, and multivariate analysis of variance, ANOVA. An example of multivariate analysis: imagine an advertiser wants to compare the popularity of 4 advertisements on a website. Then click rates could be measured for both men and women, and the relationships between variables can be measured. Let's do a recap, because this lecture was meant to include parametric and non-parametric methods, which we've discussed previously. But the basic idea of parametric methods is that there's a set of fixed parameters that determine a probability model. Parametric methods are often used for which we know the population is approximately normal, a normal distribution. Parametric tests assume a bell-shaped curve which demonstrates a normal distribution. An example: height is a normal distribution that if you were to graph the height of a group of people, one would see a typical bell-shaped curve. This is also called a normal distribution or a Gaussian distribution. When we look at non-parametric methods in statistics, are methods of statistical analysis that don't require a distribution to meet the required assumptions to be analysed, especially if the data is not normally distributed. They are sometimes referred to as distribution-free tests because they are based on fewer assumptions and do not assume that the outcome is normally distribution. The advantages are that they can be applied to a larger number of situations, can be more easily understood intuitively, can be used with smaller sample, can be used with more types of data. If we were to compare parametric and non-parametric methods, these are some of the differences. Parametric methods use a fixed number of parameters. Non-parametric methods are flexible. Parametric analyzes test group means. non-parametric test medians. Parametric are applicable only for variables. Non-parametric, both variables and attributes. Parametric always considers strong assumptions about the data. Non-parametric, fewer assumptions about the data. Parametric methods require less data than non-parametric methods. Non-parametric methods require more data than parametric methods. Parametric methods assume a normal distribution. Non-parametric methods, there is no distribution assumed. Parametric data handles intervals and ratio data. Non-parametric handle original data. Parametric assumes the results and outputs can be generated and can be easily affected by outliers. Non-parametric methods, the resultant outputs generated cannot be seriously affected by outliers. Parametric methods perform well in many situations, but its peak performance is when it's spread to each group when they're different. Non-parametrics can perform well in many situations too, but its performance is better when spread of the group is the same. Parametric methods have more statistical power. Non-parametric methods have less statistical power. In relation to computation, parametric methods are considered to be more computationally faster than non-parametric methods. So in summary, when you're hypothesis testing, parametric tests the mean, use the z-test, t-test and ANOVA. Non-parametric methods use the median, which could include the Mann-Whitley, Wilcoxon, sum test, Kreschel-Wallace, Friedman. So some of the common parametric tests that we're going to review, and we're not going to review them all, we're just going to review some of them, where you use only a normal distribution, are the t-test, the ANOVA, linear regression and the Pearson rank. The t-test is a test that tells you how significant the differences between groups are. In other words, it lets you know if those differences in treatment or before and after tests are measured mean scores. There are three main types of t-test: independent, paired and one sample. An example of the independent samples t-test is you could have a cold and try a naturopathic remedy, and your cold lasts 2 days. The next time you get sick though and have a cold, you buy an over-the-counter drug and your cold lasts longer, 5 days longer, 7 days. You ask your friends in a survey and they tell you that their colds lasted on average 3 days when they took a homeopathic remedy. What you want to know is, are these results repeatable? A t-test can tell you by comparing the mean of the two groups and let you know the probability of those results happening by chance. With an ANOVA, or an analysis of variance test, this is useful to determine the significance of differences among means of more than two groups. Appropriate to use with 3 or more groups. The variable both within and between each of the group is analysed to establish what's called the f-value. The f-value is this ratio, f equals the variation between the sample means and variation between samples. It's also used when more than one independent variable is being investigated. So an example of the ANOVA would be a clinical trial is run to compare the weight loss programs. 3 weight loss programs are considered. The first is a low-calorie diet. The second is a low-fat diet. The third is a low-carbohydrate diet. For comparison purposes, a 4th group is considered as a control group, and the control group is included here to assess the placebo effect. Weights are measured as baseline and patients are counselled on proper implementation of the assigned diet with the exception of the control group. After 8 weeks, each patient's weight is measured and the difference is computed by subtracting the 8-week weight from the baseline weight. Positive differences indicate weight loss, negative differences indicate weight gain. So an example of ANOVA: low calorie, low fat, low carbohydrate control. Common non-parametric tests. These are used when continuous data are not normally distributed, or when dealing with discrete variables. And some of these tests include chi-square, Fisher's exact, Wilcox's, Mann-Whitney, Kruskal-Wallis, Spearman rank correlation. An example of chi-square test is a statistical procedure used by researchers to examine the differences between categorical variables and the same population. It's used to compare observed results with expected results to determine if a difference between observed data and expected data is due to chance, or if it's due to the relationship between the variables. Example could be, you want to know if education level and marital status are related for all people in the country. In this example, you've got your sample, their marital status, and their educational status. The observed frequencies are located there in relation to school level and whether they're married, divorced, widowed, never married. You've got your percentages. So therefore, the question is marital status related to educational level? 46% of the respondents with middle school never married. 18% of respondents with a PhD never married. 64% of the PhD respondents are married, however. 31% for respondents just have middle school. So the finding basically tells you that more highly educated respondents get married. Before we conclude this section on data analysis, we want to think about avoiding common mistakes. And in order to avoid common mistakes, it's important to understand the research problem first, read the literature on data analysis and techniques, evaluate various techniques in regard to the research problem, choose the correct technique for the research study, and do a pilot test to evaluate the results. These lectures on basic statistics will not provide you with everything that you need. You need to do further research in order to understand what's actually going on. So in summary, a basic guide to data analysis includes breaking data down to answer research objectives and questions, then identifying phenomena to be investigated, to visualize the expected answers and validate those answers with data. Don't report on something not supported by data, and remember to analyze, not narrate. Okay, that concludes this session in an introduction to the basics. There are 7 other parts to this basic statistics learn shop. And remember, it is just the basics. And you can get access to a lot of other information on some of the excellent YouTube videos. See you in the next session, and if you think this has been of any value to you, or any of the other Dr. Manny Learn shops, recommend them to your friends and colleagues. Thanks, see you soon.